Thanks for watching this video for the KDD 2021 paper, where we embedding spaces, a comprehensive analysis on network embedding approaches for recommender systems. This is Sixiao. Okay, this paper focuses on the topic of hyperbolic space in recommender systems. We'll address the questions that when and where do hyperbolic space and hyperbolic embeddings outperform Euclidean space in recommender systems. The main contributions and findings of this paper are as follows. First, we provide theoretical analysis and empirical results to validate our three hypotheses about the effectiveness of hyperbolic space. We claim that hyperbolic space outperforms Euclidean space on distance models, low density datasets, and small latent sizes. Second, we address the drawbacks of hyperbolic space and give comments on when and where to use hyperbolic space. Third, we propose a metric learning-based social recommendation method, social collaborative metric learning, and its hyperbolic version, HSAML, and validate our hypotheses on them. We also show that hyperbolic space has state-of-the-art performance by comparing HSAML with other baselines on two benchmark datasets. Okay, first, let me introduce the background of this work. Latent space models such as matrix factorization-based models and metric learning-based models are widely used in graph-based recommender systems. Conventional latent space models are built in Euclidean space. However, Euclidean embeddings suffer from a high distortion when embedding scale-free and hierarchical data. The distances of users and items are not likely to be preserved when embedded into Euclidean space. It is necessary to increase the latent size in order to reduce the distortion. But as the latent size increases, the resources needed to train and store the model also increase. Therefore, a more expressive latent space is needed to solve the problem. Recently, hyperbolic space has been explored as a new latent space and has shown impressive performance. It outperforms Euclidean space in many domains, including natural language processing, link prediction and node classification, and top-line recommendation. A key property of hyperbolic space is that it expands faster than Euclidean space. Euclidean space expands polynomially, while hyperbolic space expands exponentially. In other words, the data capacity of hyperbolic space is larger than Euclidean space. Another important property is that it can preserve the hierarchies of data, which is common in many real-world data such as texts, e-commercial networks, and social networks. Although hyperbolic embeddings are gaining great attention for recommender systems nowadays, it is not clear under what circumstances the hyperbolic space should be considered. As a current trending topic of hyperbolic embeddings, practitioners are indiscriminately attempting to transfer variants of existing algorithms into hyperbolic geometry, regardless of having strong motivations. Therefore, it is timely needed for a fair comparison and analysis on existing recommendation algorithm in hyperbolic space. Our work aims to fix the gaps and provide a comprehensive analysis on hyperbolic space and hyperbolic embeddings for recommender systems. Again, our contributions are as follows. First, we provide theoretical analysis and empirical results to validate our three hypotheses about the effectiveness of hyperbolic space. Second, we address its drawbacks and give some comments. Third, we propose and evaluate social collaborative metric learning. Before going to our hypothesis and experiment results, I would like to give a brief introduction to the latent space models and the Poincare ball model. Hyperbolic embeddings are usually learned with latent space models, which are models that are capable of learning node embeddings. Based on how to model relations between nodes, latent space models can be split into two categories, projection models and distance models, where they use the inner product and the distance, respectively, to measure the similarities of embeddings. One of the most representative methods for projection models is matrix factorization, and for distance models, metric learning should be the most well-known method. In order to apply hyperbolic space on latent space models, we need to know how to compute the hyperbolic distance and hyperbolic inner product. In our paper, we focus on the Poincare ball model, which is the most suitable hyperbolic model for learning hyperbolic embeddings. Here is an illustration of the structure of the Poincare ball model. Each polygon has exactly the same size in the hyperbolic space, so its data capacity is actually much larger than Euclidean space. The distance and the inner product of two vectors in the Poincare-Ball model can be easily calculated with Euclidean operations. For example, the first equation here denotes the distance of two vectors in a Poincare-Ball model with constant curvature -1. All we need are the Euclidean coordinates and Euclidean norms of the target points. After that, we can utilize the hyperbolic distance to learn models such as metric learning-based ones. Now, let me introduce three hypotheses we proposed regarding the performance of hyperbolic space. Our empirical experiments are designed to evaluate the correctness of them. Here I only list the important rationalities of the hypothesis. Please refer to our paper for a more detailed explanation. First, we argue that distance models are more suited for learning hyperbolic embeddings than projection models. The distribution of the embeddings in the two models is different after convergence. The embeddings in projection models usually gather around the origin, making it hard to make use of the outer part of the hyperbolic space where the capacity is the largest, thus reducing the expressiveness. Furthermore, distance models can easily capture the hierarchical information. Therefore, distance models should be a better choice for learning hyperbolic embeddings rather than projection models. Second, we think hyperbolic space is more powerful compared to Euclidean space when the density of the dataset is small. Hyperbolic space is naturally capable of extracting the hierarchical information from datasets. It can use such hierarchy to help learn the node embeddings more effectively. Therefore, it can have a relatively good performance even the density is low. Third, we assume that the performance of hyperbolic space is better than Euclidean space when the latent size is small. But as the latent size increases, the performance of Euclidean space becomes comparable with hyperbolic space. The expressiveness of hyperbolic space is much larger than Euclidean space. To fully capture all the hierarchical information in the dataset, the number of dimensions needed in hyperbolic space is much smaller than Euclidean space. On the other side, as the latent size increases, the distortion of Euclidean space will reduce and become similar with hyperbolic space. Eventually, Euclidean space will have a similar performance with hyperbolic space. Now, let me introduce our experiments. We evaluate the correctness of the three hypotheses on both general item recommendation domain and social recommendation domain because of their popularity and long-tail distribution. We compare the performance of hyperbolic space and Euclidean space on the 5 baseline models in this table. MFBPR is a well-known matrix factorization-based method. CML, which stands for Collaborative Metric Learning, is a metric learning-based general item recommendation model. DMF, which stands for Deep Matrix Factorization, is a model that incorporates matrix factorization and deep neural networks. Trust SVD and SOREC are two social recommendation models based on matrix factorization. For datasets, we use 6 popular benchmark datasets. Movie-length 1 million and movie-length 100,000 are from the popular movie-length dataset. Automotive and cell phones are subsets of the Amazon dataset. Opinions and Shell are two public available datasets for social recommendation. Notice that the densities of the two movie-length datasets are much larger than others. We will compare their performance to evaluate the hypothesis regarding dataset density. For evaluation metrics, we use hit ratio and normalized discounted cumulative gain for top-line recommendation models, and use mean absolute error and rooted mean square error for rating prediction models. Now let's look at the experiment results and evaluate our hypothesis on general item recommendation scenario. We will show the results of social recommendation scenario afterwards. First, we show the influence of the density of datasets. Let's take CML as an example. The pictures here in the first row are HRs and NDCGs for movie lengths, and the pictures in the second row are for automotive and cell phones. Recall that density of movie lengths is much larger than automotive and cell phones. Okay, we may just focus on the pink and red lines in these pictures, which represent the HRs and NDCGs of the hyperbolic space and Euclidean space respectively. when the latent size is 10. For movie lengths, the pink ones and the red ones are very close to each other, while for automotive and cell phones, the pink ones greatly outperform the red ones. In other words, hyperbolic space and the Euclidean space have a similar performance on movie lengths. However, hyperbolic space clearly outperforms Euclidean space on automotive and cell phones. This supports our hypothesis that hyperbolic space is more powerful compared to Euclidean space when the density of the dataset is small. Then let's see how the latent size influences the performance of a hyperbolic space. Again, we use the result of CML as an example. Let's focus on the pictures in the second row. We can observe that the improvement of hyperbolic space over Euclidean space decreases as the latent size increases. When the latent size is 10, hyperbolic space significantly outperforms Euclidean space. However, as the latent size increases to 50 and 100, the performance of Euclidean space becomes comparable with hyperbolic space. This is consistent with our hypothesis that the performance of hyperbolic space is better than Euclidean space when the latent size is small, but as the latent size increases, the performance of Euclidean space becomes comparable with hyperbolic space. At last, let's see how hyperbolic space performs in distance models and projection models. Here we show the results of two representative baseline methods, CML and MFBPR. Let's first look at the result of CML. From these pictures, we can observe that Euclidean space can never outperform hyperbolic space. And hyperbolic space always has larger or equal HR and NECG compared with Euclidean space. Recall that CML is a distance model, which suggests that the distance model is a good choice for learning hyperbolic embeddings. However, what about projection models? Does hyperbolic space still outperform Euclidean space in projection models? To answer this question, let's take a projection model as an example. For example, MFBPR. To quickly capture the idea, let's look at picture E here, which is the result of HR on automotive. The dark green line represents the result of Euclidean space with the latent size is 100, and the light green line represents the result of hyperbolic space when the latent size is also 100. We can observe that the dark green line is above the light green line. In other words, Euclidean space achieves a better hit ratio than hyperbolic space. This suggests that Euclidean space should be a better latent space than hyperbolic space for projection models. Therefore, our hypothesis regarding distance models and projection models is proved to be true that distance models are more suited for learning hyperbolic embeddings than projection models. Now that we have seen that the experiment results on general item recommendation scenario are consistent with our three hypotheses, what about social recommendation scenario? Recall that among our baselines, we have two social recommendation methods, namely trust SVD and SOREC. However, they are both projection models, and there is a lack in using distance models to solve top-N social recommendation tasks in existing literature. Therefore, we here propose a new metric learning-based social recommendation method for top-N recommendation, which is called as social collaborative metric learning, a generalized form of collaborative metric learning. The loss function of SAML is composed of two parts. One is item size loss, another is social size loss. The item size loss is the same as the loss of CML, whose goal is to push the connected user item pairs close to each other and push non-connected pairs away from each other. The social size loss is similar to the item size loss, whose goal is to push the connected user-user pairs close to each other and push non-connected pairs away from each other. Ideally, socially connected users and their interacted items will be pushed close to each other in the embedding space. Now let's see how hyperbolic space performs in social recommendation scenario. First, we show the results of SAML. We can observe that the experiment results are still consistent with our three hypotheses. First, since SAML is a distance model, the hyperbolic space should outperform Euclidean space on it, and the results also demonstrate it. Second, we can observe that as the latent size increases, the performance of Euclidean space gradually catches up with hyperbolic space. This is consistent with our hypothesis regarding the latent size. Third, recall that the density of impedance and shell are quite small, so it is reasonable that hyperbolic space has a significant advantage over Euclidean space in these pictures. Then let's look at the results of Sorek and Trust SVD. Since they are designed for rating prediction tasks, we report MAE and RMSE here, where a smaller value indicates a better prediction performance. We can observe that in all four pictures, the errors of hyperbolic space are bigger than Euclidean space, which means that hyperbolic space cannot outperform Euclidean space. This is reasonable because both Sorek and Trust SVD are projection models. So far, we have evaluated the correctness of our three hypotheses using empirical experiment results. Here, we further compare our HSAML with some baseline recommendation methods to demonstrate the great potential of hyperbolic embeddings. In this table, we show the HRs and DCGs of several baseline methods and our HSAML on shell and impedance. The last column is HSAML. The best results are the bold-faced, and the second best are underlined. We can observe that HSAML has comparable performance with the state-of-the-art baselines such as RML DJTs and SAMN. However, HSAML is only a very simple distance model, whereas the SAMN and RML DJTs are much more complicated because of the memory modules and the graph attention network units. This demonstrates the superiority of hyperbolic space over Euclidean space. Future works to design a customized model for hyperbolic space may produce a model that outperforms all existing approaches. So that's all for our experiments. Now we address some drawbacks of hyperbolic space. First, it has high computational complexity. When using hyperbolic space, the exponential map and logarithmic map are necessary whenever we apply a simple operation to the embedding, such as matrix multiplication and bias addition. This makes the algorithm computationally inefficient. Second, since the computation involves inverse hyperbolic functions, it is extremely easy for the denominators to be zero or infinite. Due to the precision of the device, it is necessary to keep values wherever might become invalid. At last, we give some comments on when and where to use hyperbolic space. First, distance models are more suited for learning hyperbolic embeddings than projection models. Second, if the density of the dataset is large, Euclidean space should be a better choice because it has a comparable performance with hyperbolic space, and the computational complexity is low. When the density is low, hyperbolic space is more preferable because it will have a much better performance than Euclidean space. Third, we should choose the appropriate latent size. In most cases, hyperbolic embeddings only need a relatively small latent size to achieve good performance, which can help to save resources. Okay, for future directions, we will try to explore the effectiveness of hyperbolic space on other recommendation scenarios, such as sequential computation. Also, as we said before, hyperbolic space is of great potential in recommender systems. Therefore, we expect to design a dedicated hyperbolic recommender system, which will have state-of-the-art performance. Okay, this is the end of this video. Thanks for your watching. Please refer to our paper for more detailed information regarding this work. And feel free to contact us by email. And also our code is available at GitHub. Thank you.